Oh, hey.
Very good. So first speaker is Jerry.
This is how it works. So hello everyone. So this work is essentially about battery market power and strategic behavior. You can see from California here the noticeable growth of battery capacity just in the last few years. And this has changed the operations of the grid because it is like having a lot of solar. It is good because it is shifting energy from off-peak when it is cheap to peak where it is expensive. But when it is big, you have to wonder whether there can be strategic behavior and whether the charge and discharge decisions that they do to maximize profit would align or misalign with the socially optimal goal of minimizing costs. We consider three battery regimes: no battery, centralized, minimizing cost, and decentralized. We show that the problems are both convex and you can solve them in closed form. Our contribution here is also on the modeling side, proposing an analytical models that are trustable and yet rich enough to capture the salient features of the market. And we show that the decentralized solutions show three types of distortions. One is quantity withholding, or you are not smoothing the peak versus off demand as much as you should compared to socially optimal. The shift from day ahead to real time, because we have sequential market clearing, and you are essentially hiding your capacity until it is really needed, which screws up the day ahead commitment process. And the real-time responsiveness, which is that you have inherent volatility in demand that the batteries should be smoothing, and you're not smoothing that enough. You can quantify these precisely in terms of market parameters, and you can also quantify this in a single number of the price of energy metric. And you can show that the price of energy is always between 9/8 and 4/3 for every market parameter. And that if you have more faster generators, that is better. Our calibration shows that these things are also significant in practice. Thank you.